Space is not empty. It's a vast, dynamic environment filled with wonders and mysteries that continue to baffle and inspire scientists and dreamers alike. It's filled with giant clouds of gas and dust known as nebulae. These nebulae are the birthplaces of stars and planets, the cradles of cosmic creation. We call these giant molecular clouds. They are immense, stretching across light years, and are composed of the basic building blocks of the universe. These clouds are cold and dark, but they are where stars and planets are born. Despite their frigid temperatures and shadowy appearance, they are teeming with potential. Imagine a cloud so big it could hold 1,000,000 suns. These colossal structures are the nurseries of the cosmos, where the seeds of stars and planets are sown. That's a giant molecular cloud. Within these clouds, the delicate dance of gravity and pressure begins the process of star formation. These clouds are mostly made of hydrogen and helium, the simplest elements in the universe. Hydrogen, the most abundant element, serves as the primary fuel for stars. They also contain small amounts of other elements like carbon, oxygen, and iron. These heavier elements are forged in the hearts of stars and scattered across the galaxy when those stars die. These heavier elements are the building blocks of planets like Earth. Without them, the complex chemistry needed for life as we know it wouldn't be possible. Think of these elements as the ingredients for making a cake. Just as you need a variety of ingredients to bake a cake, the universe needs a mix of elements to create planets and stars. You need flour, sugar, eggs, and so on. Each element plays a crucial role in the recipe of cosmic creation. Giant molecular clouds are dynamic places. They are constantly shifting and changing, influenced by various forces in the galaxy. Shock waves from exploding stars or the gravity of passing stars can squeeze these clouds. This compression is a critical trigger for star formation. This squeezing is important. It starts the process of star and planet formation. As the cloud collapses under its own gravity, it begins to heat up and form new stars. Imagine squeezing a lump of dough. The pressure causes it to change shape, just like the pressure in a molecular cloud leads to the formation of stars. Eventually it starts to take shape. In the case of molecular clouds, this shape is a new star, surrounded by a disk of gas and dust that can form planets. The universe is filled with these giant star-forming clouds. Each one is a potential birthplace for new stars and planetary systems. Studying them helps us understand our own origins. By observing these clouds, scientists can learn about the processes that led to the formation of our own solar system. They are a reminder that we are all connected to the cosmos. The elements that make up our bodies were forged in the hearts of stars, linking us to the universe in a profound way. As a giant molecular cloud is squeezed, something amazing happens. This cloud, composed of gas and dust, is the birthplace of stars. These clouds are often found in the spiral arms of galaxies, where they can span hundreds of light years across. The process begins when external forces such as shock waves from nearby supernovae or collisions with other clouds compress the molecular cloud. This compression triggers the gravitational collapse of the cloud. Gravity takes over. Gravity pulls the gas and dust towards the center of the cloud. This inward pull is relentless, drawing more and more material into an ever-tightening core. As the particles move inward, they collide and stick together, forming clumps that grow in mass and density. The gravitational force becomes stronger as the mass increases, accelerating the collapse. As more material falls inward, the center gets denser and hotter. The temperature in the core rises dramatically, reaching millions of degrees. This intense heat is a result of the gravitational energy being converted into thermal energy. The core becomes a hotbed of activity, with atoms colliding at high speeds, creating a pressure that counteracts the force of gravity. Think of it like a snowball rolling down a hill. It gets bigger and faster as it collects more snow. Similarly, the core of the molecular cloud gathers more material, increasing its mass and gravitational pull. This runaway process continues until the core reaches a critical point. Eventually, the center of the cloud gets so hot that it ignites nuclear fusion. This is the moment when hydrogen atoms in the core begin to fuse into helium, releasing a tremendous amount of energy. This energy radiates outward, creating a balance between the inward pull of gravity and the outward pressure from the fusion reactions. This is when a star is born. A star is basically a giant ball of gas held together by its own gravity. The newly formed star shines brightly, marking the end of the collapse phase and the beginning of its life as a main sequence star. The star will continue to burn hydrogen in its core for millions to billions of years, depending on its mass. The newborn star blasts out light and heat. This pushes away some of the surrounding gas and dust. The intense radiation and stellar winds from the young star clear out the immediate vicinity, creating a bubble of space around it. However, not all the material is expelled. However, gravity holds on to most of the material. This leftover material forms a swirling disk around the young star. This disk, known as a protoplanetary disk, is the birthplace of planets, moons, and other celestial bodies. The material in the disk gradually coalesces to form planetesimals, which can eventually grow into full-fledged planets. This is called a protoplanetary disk. We'll talk more about this disk in the next section. The formation of planets from this disk is a complex process that involves accretion, collisions, and gravitational interactions. It's a fascinating journey from dust to planets. The birth of a star is a violent and beautiful process. It's a reminder of the incredible forces at work in our universe. From the initial collapse of a molecular cloud to the ignition of nuclear fusion, the journey of star formation is a testament to the power of gravity and the dynamic nature of the cosmos. The protoplanetary disk is a fascinating place. It's where planets are born. This disk is made up of the same gas and dust that formed the star. It's incredibly hot near the star and cooler farther out. Imagine a pizza fresh out of the oven. The center is hottest and the edges are cooler. The disk is constantly spinning. This spinning motion helps to flatten the disk out over time. Think of spinning pizza dough in the air. It flattens out into a circle. This flattened disk is the perfect environment for planet formation. Within this disk, tiny dust grains start to stick together. This is the beginning of planet formation. It's like building a sandcastle, one grain of sand at a time. Over millions of years, these tiny grains will grow into planets. The protoplanetary disk is a busy and chaotic place, but it's also a place of incredible beauty and wonder. Inside the protoplanetary disk, tiny dust grains are constantly moving and colliding. These grains are the remnants of ancient stars, composed of elements like carbon, silicon, and iron. They are the raw materials from which planets are born. Imagine a crowded dance floor with everyone bumping into each other. Each collision is like a tiny handshake, a brief interaction that can lead to something bigger. These collisions are key to planet formation. Without them, the dust grains would remain isolated, drifting aimlessly through space. When dust grains collide at low speeds, they can stick together. This sticking is due to electrostatic forces, much like how a balloon rubbed on your hair can pick up small pieces of paper. This process is called accretion. Over time, these small clumps of dust grow larger as they attract more particles. Think of it like static cling. Just as static electricity can make small objects stick together, the forces at play in the protoplanetary disk cause dust grains to clump. The grains are attracted to each other, forming larger and larger clumps. These clumps are the seeds of future planets. Over time, these tiny clumps grow bigger and bigger. As they grow, their gravitational pull increases, allowing them to attract even more material. As these clumps grow, their gravity gets stronger. This stronger gravity helps them pull in more dust and gas from the surrounding disk. They start to attract more dust and gas from the surrounding disk. This additional material helps the clumps grow even faster. This accelerates their growth even further. The more mass they accumulate, the more powerful their gravitational pull becomes. Imagine a snowball rolling down a hill, getting bigger and bigger as it picks up more snow. This is similar to how these clumps grow in space. Eventually, these clumps grow large enough to be called planetesimals. These are the building blocks of planets, the first step in the long journey to becoming a fully formed world. Planetesimals are like the building blocks of planets. They are the initial large structures that will eventually merge to form planets. They are still small, maybe the size of an asteroid, but they have the potential to grow much larger, but they are on their way to becoming planets. Through continued collisions and accretion, they will gather more material and grow. The process of planetesimal formation is a crucial step in the birth of planets. Without planetesimals, there would be no planets. It's a testament to the power of simple processes like collisions and gravity to create complex structures. From tiny dust grains to massive planets, the journey is a remarkable one.